In today's video, we will see what is the impact of transformer no load voltage in load flow and short circuit studies using ETAP. And I have modeled one simple network which consists of this grid. Grid, this is 11 kV, X by R ratio 14, and short circuit current is 40. 11 kV, this transformer, this is 2 MVA transformer, 11 bar 0.415 kV. Impedance is typical impedance I have considered, and X by R ratio also. And in LV system, 415 volt system, I have connected 1 MVA load. This is 1 MVA load, 80% motor, 20% static load I have considered. So we will see some of the case studies. What is the impact? What is the impact of this transformer voltage ratio, primary side voltage, secondary side voltage? If we change this voltage or the no load voltage, sometimes you will see in the transformer data sheet that it is 11 kV per 0.433 kV, 0.433 kV, whereas the bus is 0.41 kV. Okay, so what will be the impact? If we consider this transformer secondary side is 415 volt, and again if we consider secondary side this transformer no load voltage as 433 volt, what will be the impact with respect to load flow and short circuit studies? So let's run this load flow. Let's see. So as you can see, this bus voltage is at LV level, bus voltage is 97.88 percentage. This 97.88 percentage. Now if we consider this transformer secondary side no load voltage as 0.433 kV without changing any other parameters, let's see what will happen. So now it is 97.88%. Now the bus voltage is increased more than 100%. Now it is 102.1%. So definitely there is impact. There is an impact. So this thing we should not ignore whenever we are modeling in ETAP. Based on the transformer manufacturer dataset, we have to consider whether the transformer secondary side no load voltage is the bus voltage, means 415 volt, or 433 volt, because it will have an impact. It was 97.8%. Now it is more than 102%. This is one of the aspect. And now we will check also, instead of changing this, let's say it is 415 volt only, 0.415 kV, but in the secondary side this is 5% extra, means 11.5 kV. Though this bus voltage, upstream bus voltage is 11 kV, the transformer primary side rating is 11.5 kV. So what will happen if we run the load flow? The bus voltage is decreased and it is showing red alert, means it is less than the acceptable limit 5%. Hence the bus is under voltage, right? So these two things, whether the transformer primary side voltage is the bus voltage or more than that, whether the secondary side transformer no load voltage is the bus voltage, secondary side bus voltage, or some other values. So we need to be very careful about this, because based on that our power system network result will be different after the simulation. It's a simple network, but whenever, if you don't have the concept, whenever you will handle a complex network, that time you may face some troubles. You will not be able to understand where is the problem. So because of these small changes, you can see the bus voltage is rising off or going down, maybe in that case you will try to change this transformer tap in that case. But before changing the transformer tap, before touching that transformer tap, off circuit tap changer, probably this one will be off circuit tap changer. So before touching that tap, you should be checking all these parameters because this transformer primary side and secondary side voltage, these are important. Okay, now we will check from the short circuit perspective what what may be the change, what will be the impact. let's let's take it as the normal value 11 bar 0.415 kV. I'm not changing any other parameters. Okay, so what I'll do, simply I'll run this short circuit. Okay, so this is the fault level at 415 volt. Bus fault level is 53.219 kilo ampere. 53.219 kilo ampere. Now let's change this as 433 volt. So previously it was 53.219, 53.219. Now it is 49.445 kilo ampere. Previously it was 53.219. Now it is 49.445 kilo ampere. That means the short circuit current contribution from the source grid towards this LV bus is reduced. Why it is reduced? Why it is reduced? Because the transformer secondary side, means transformer no load voltage, is increased. And if you can recall that formula, the Z new Z per unit new value, that is equals to old per unit impedance value multiplied by base kV old by base kV new whole square. So base kV old is 0.433 and base kV new is 0.415. That means the numerator is more larger than the den, so num is more than den, so the impedance value is increased. So what is the formula? Z per unit new equals to Z per unit old into base kV old by base kV new whole square into 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 base MVA new by base MVA old. So what will happen? The overall impedance, the overall impedance provided by this transformer is increased. So if that if that if that equivalent impedance is increased, that means the short circuit current will reduce. So that is why the short circuit current is reduced from 53 kiloamps to 49.445 kiloampere. Okay, now if we change this rating, this primary side as 11.5 and secondary side is 415 volt, that's the secondary side bus voltage, what will happen? We will see that. So now it is, so previously it was, if it is 11 bar 0.415 kV, it was 53.219, as you can recall, it was 53.219. Now let's run this. It is 53.4 kiloampere. That means it is increased. That means it is increased. So why it is increased? The fault current is increased because of the same explanation as I have given for the previous case. So the fault current is decreased. Fault current contribution is decreased. Fault current contribution by the source grid is decreased. So in this way, you have to check, and you should have the knowledge uh, for changing the transformer primary and secondary side or the no load voltage, what is the impact on the load flow study case and short circuit study cases. So if you have this knowledge, you will be able to understand the nature or the behavior of the power system network. So I hope this video was helpful and it will value it will add some value.